So the title of this work is Numerical Evaluation of the Adhesive Effect on the Peel Strength of Aluminium T-Joints. This work is the result of a master's thesis of a student of mine, João Lopes. The layout of this presentation begins with the goals of this work, then a short introduction to the topic of adhesively bonded joints and numerical modeling, experimental validation of the numerical technique, and then a numerical study on the T-joints considering the geometries, materials, and boundary conditions, the cohesive zone modeling technique for the cohesion assessment, and the results of the numerical analysis. I will conclude with the conclusions and future work proposals. The main goal of this work is to carry out a numerical study of T-adhesively bonded joints between aluminium adherents, considering 4 geometric variables and 3 different adhesives with different characteristics. We want to analyze the stress distributions, damage variable, strength, and the dissipated energy at failure of the joints, and we want to propose the ideal adhesive for applications where the T-joints are mainly under peel loadings. A short introduction to the topic of adhesively bonded joints. The reinforcement joints, as the ones that we see in this slide, they allow for a reduction in peel stresses. They are ideal to bond adherents with different thicknesses, and they add to the structural stiffness under bending. T-joints in particular, they have a significant bonded area, and we must take attention that we need to minimize peak peel stresses to prevent premature failures. The adhesive joints in particular have some applications, for example, in the automotive and aeronautical industries, and they are in constant development. They are also widely used in the scope of composite material bonding, although this is not the scope of this work, and they are structural joints. Experimental validation of the CZM technique was initially carried out by comparing the experimental and numerical results of T-joints bonded with different adhesives. In this validation study, the main parameter that was varied was the T-adherent thicknesses, the thickness of the part which supports the load. And here we can see the results for the case of a brittle adhesive, which is the AV138, which is also studied in the numerical part of this work. And we can see that the numerical models with the proper pre-processing conditions, which replicate the experimental tests, were able to simulate accurately the behavior of the joints. So with this in mind, we are now going to perform a numerical study considering 4 different parameters, namely the base thickness with values between 1 and 4 millimeters, the thickness of the T component with values between 0.5 and 2.5 millimeters, overlap lengths between 10 and 40 millimeters, and radius of the T component between 3 and 12 millimeters. On the other hand, the thickness of the adhesive was kept constant at 0.2 millimeters. In this slide, you can see the materials used in this work, a medium strength aluminium alloy, 6082, which was characterized for insertion of the respective properties in the numerical models, and 3 adhesives were considered, ranging from brittle, the AV138, which is a strong but brittle adhesive. The 2015 is also an epoxy adhesive, but with a tensile strain of 5% at failure, and the Sika Force is a polyurethane adhesive with a smaller strength, but with a ductile behavior. The pre-processing conditions were defined to replicate the experimental analysis, namely the boundary conditions, the geometry of the materials. The mesh was created to enable that it is not dependent on the mesh, the results, and a triangular law cohesive zone modeling was considered to replicate or to simulate the damage in the adhesive layer. It may be a simplification for the case of ductile adhesives, but it is ready in the most commercial software. We have a smaller amount of parameters to define, and it provides sufficiently accurate results in most conditions. A stress analysis was initially carried out for the joints, considering the four geometric parameters, and beginning with the peel stresses. And here we only consider the RLD 2015 as an example. You can see, for example, that as we increase the thickness of the base adherent, we have a reduction of the peak peel stresses at the edge of the adhesive because the joint becomes stiffer. On the other hand, if we increase the thickness of the T part, we have an increase also of the peel stresses of the joint because of the concentration of stresses at this same region that occurs due to the higher stiffness. On the other hand, if we increase the overlap length, we have a corresponding increase on the peak stresses, and this is what occurs, for example, in single lap joints because of the higher effects of deformations, lateral deformations. And finally, if we change the radius of the T component, we don't have a significant modification of the peak stresses at the edge of the adhesive, although there are some changes at the region of the radius, but this does not affect the results. The damage variable of the cohesive elements was also addressed, and we can see that there is a significant difference for all of the parameters. For example, for the adherent thickness, for the T thickness, inclusively for one of the conditions for the overlap length, we have failure at two distinct regions, but only damage at the middle region. It's what happens in this case for an overlap length of 40 millimeters, and also some variation of the damage by changing the radius of the T component. Here we can see the maximum loads, once again for the four variables. Between the three adhesives, the Sika Force 7752 always gave the best results because although it is less strong, it is ductile and it works better under these conditions in which we have stresses concentrated at a very small region. Between the different parameters, we can see that the base adherent has an effect on the strength of the joints, except for over 2 millimeters for the 7752 adhesive. The thickness of the T component also increases the strength of the joint, except for the very brittle adhesive, because this adhesive cannot withstand the high stress concentrations that increase with the thickness of the T. The overlap length also tends to increase the strength of the joints, except for the brittle adhesive, and this is normal because we are increasing the bonded area. And finally, the T radius does not affect significantly the two RLD adhesives, but it increases the strength of the Sika Force adhesive because it increases load transfer at the region of the radius. Finally, the energy prediction, which is the area beneath the load displacement curves. It is also a measure of performance of the joints. It somehow follows the maximum load of the joints, but here we have to take into consideration that in the joint geometries in which we have plasticization of the adherent, this affects or it increases the energy dissipated at failure. So here the main influences are for the Sika Force 772 adhesive, for the adherent thickness and T thickness, and in the case of the overlap length, we see an effect for the 2015 and 7752, while the T radius only affects the 7752 adhesive. And this concludes the presentation. Here I have a summary of all the conclusions divided by the effect, but here the main important is that we could see clearly which is the best adhesive for this application, which is the polyurethane adhesive, and we could also see the effect of each one of the parameters after validating CCM technique for this particular application. So thank you very much for listening to me. I finished my presentation. Thank you.
Thank you, Professor Campilho. Any questions? No one? Just a curiosity. In your model, how do you take into account the influence of the surface roughness, for example, of the aluminium into joint?
Okay, thank you for the question, Vittorio. Well, in this model, we consider that the adhesive is perfectly bonded to the adherents. So we have only a single component, which we divide into partitions, and then we give, for example, one partition for the adhesive and one partition for the aluminium. And so it is assumed that the bonding is perfect. In the experiments, we just have to assure that we don't have failure at the interface. Which is with the aluminium, the surface preparation is simple. For example, if we perform a sandblasting with specific conditions and then we degrease, for these adhesives, we assure that we have failure in the adhesive.